Hey class, Mr. Hanji here. For today's lesson, we're going to be taking a look at section 4.1, which is going to do with identifying and graphing sequences. Now, for today's lesson, we have two learning goals. And our first learning goal is you will be able to find terms in a sequence given by an explicit or recursive rule. And you will be able to construct and graph a sequence based off a description. So today we're going to look at sequences, different components of them, and how to go through and find terms based off that sequence. Now, before we get into examples, let's talk about a little bit of terminology. So, a go-kart racing track charges $5 for a go-kart license and $2 for each lap. If you list the charges for 1 lap, 2 laps, 3 laps, and so on, in order, the list forms a sequence of numbers 7, 9, 11, 13. Now, the reason why it's 7 and not 5 is because you have to have a go-kart license, which is $5, and then it's $2 for each lap. So for 1 lap, you had to have already bought the license, and then it's $2 for the first lap, and then it increases in increments of 2. So my not starting point, but my kind of 0 point would be $5. My starting point after 1 lap is 7, and then it increases in increments of 2. Now, a sequence is a list of numbers in a specific order. So this right here is a sequence, just a list of numbers in a specific order. Each element in a sequence is called a term. In a sequence, each term has a position number. In the sequence 7, 9, 11, 13, the second term is 9 because it's the second number in the sequence. So whenever you hear us talk about terms, in this module, we're talking about a number in the sequence. And when we tell you the specific term, we're talking about that number in the order. So its position number is 2. All right, now before we jump into our first example, there is one last bit of stuff to talk about, and let's talk about what an explicit rule is. So an explicit rule for a sequence defines the nth term as a function of n for any whole number n greater than 0. Explicit rules can be used to find a specific term in a sequence without finding any of the previous terms. So what this is going to kind of look like is I'm going to give you a function or an equation, and I'm going to ask you to go through and find either the first 4 terms or find a specific term. And you're going to use that rule to help you just go through and find it. Now, explicit, if you know what term you're looking for, you just have to plug that number in. When we talk about a recursive rule, you have to know all the previous numbers before you can get there. And we'll talk about recursive here in a bit. All right, so let's go ahead and take a look at example 1. So let me go ahead and move this up. For example 1, it asks us to go through and write the first 4 terms of the sequence defined by the explicit rule. So one thing I want to point out, and it will make more sense when you see it for recursive, but explicit would be f of n equals 3n plus 2 in this case. It's just where you have n, and it's either going to be multiplied, divided, added, or subtracted. You'll notice a very vast difference with recursive. So when we talk about whether something's recursive or explicit, it should become pretty apparent. Now, for A, we have to go through and write the first 4 terms of the sequence. That means the first 4 terms we would have 1, 2, 3, and 4. So that means I need to plug 1, 2, 3, and 4 in for n, and then go through and solve to find my first 4 terms. So let's go ahead and do it for the first term. F of 1 is going to be my first term. That means I'm going to plug 1 in for n. So it's going to be 3 times 1 plus 2. Now you can either go through and solve it one at a time, or you can go through and set up all of your equations for terms 1, 2, 3, and 4, and then solve. Let's go ahead and just solve it one at a time before we jump into all the others. So I'm going to use my calculator to do this. We have 3 times 1 plus 2. So we're going to do 3 parentheses 1 plus 2. And we end up with 5. We do f of 2. It's going to be 3 times 2 plus 2. So 3 times 2 plus 2 is 8. F of 3 is going to be 3 times 3 plus 2. And 3 times 3 plus 2 is 11. And then f of 4 is going to be 3 times 4 plus 2. 3 times 4 plus 2 is 14. And we will stop there. So I have my first 4 terms. I have plugged in 1, 2, 3, and 4 into my explicit rule. We've gone through and discovered my first 4 terms. So my first 4 terms of the sequence is 5, 8, 11, and 14. And that's our answer. So if it asks you to go through and identify the first 4 terms of an explicit rule, you're just going to take 1, 2, 3, and 4, plug it in, go through and solve, and then you go through and get your answers. So my answer for number 1A is 5, 8, 11, and 14. All right, for part B, we're going to go through and do the same thing. We just have a different rule. Now for B, it's f of n equals n to the power of 2 plus 2. So n squared plus 2. So we're going to go through and plug in 1, 2, 3, and 4 for n, and then go through and solve. All right, let's go ahead and do that. So f of 1 is 1 to the power of 2 plus 2. And for this one, I'm going to go through and write all of them out, and then we'll go through and solve them. F of 2 is 2 to the power of 2 plus 2. F of 3 is 3 to the power of 2 plus 2. And then f of 4 is 4 to the power of 2 plus 2. All right. So now that I have them all set up, we're going to go through and calculate the values for each term. So if we look at the first term, we have 1 to the power of 2 plus 2. And we end up with 3. If we do 2 to the power of 2 plus 2, we get 6. 3 to the power of 2 plus 2 is 11. And then 4 to the power of 2 plus 2 is 18. So my terms are 3, 6, 11, and 18. And those are going to be my first 4 terms of the sequence, and thus my answer. Now, the sequence does go on to infinity for infinite amount of terms. We just need to plug it in for the first 4 terms for parts A and B. All right, so that is how we go through and find the first 4 terms of the sequence defined by the explicit rule. And that is how we go through and do that for part 1, or example 1, parts A and B. Now, parts C and D is a touch different. It's not as extensive, but it's a little different and something I want to take a look at before we move on. So for C, we have the explicit rule, f of n equals 3n squared plus 1, and they want us to find the 6th term. So sometimes they want you to go through and find the first 4 terms. They want you to go through and find the first 4 terms. You do what we just did in parts A and B. If they want you to find a specific term, what we're going to do is take the number, which in this case would be 6, and we're going to plug it in for n. So if you were given an explicit rule where it looks like this, where it's f of n equals something times n plus or minus something, when that is the case, you just have to plug the number in. So we're going to have f of 6 equals 3 times 6 to the power of 2 plus 1. And all we have to do is just go through and solve. So let's go ahead and set that up for this one. So we have 3 times 6 to the power of 2 plus 1. And we end up with 109. And that is our answer. So you don't have to go through and find the first term, the second term, third term, fourth term, fifth term, and then finally the 6th term. We can just go ahead and jump to the term that we want to find. Now 109 comes from the fact that 6 to the power of 2 is 36, and then 3 times 36 is 108. 108 plus 1 is 109, as our calculator showed. And that is how you go through and do that for part C. Now, real quick, for part D, it wants us to go through and find the 15th term. Okay, it doesn't matter how large the term, we can just go through and plug in the number, whether it's the 6th or the 15th or the 125th term. You just need to plug that number in, and then you can get your answer. So let's go ahead and do this for the 15th term. So we're going to plug 15 in for n. So f of 15 is 4 times 15 minus 3. So in our calculator, we're going to do 4 times 15 and then minus 3. And we end up with 57 as our answer. So the 15th term of the sequence is 57, and that comes from the fact that 4 times 15 is 60. 60 minus 3 is 57. And that is how we do example 1. Alright, so that is an explicit rule, and that's something I want you to keep in mind, that when you have an explicit rule, you can just plug that number in to then go through and solve. Now, the other thing we talked about in the learning goal was recursive rules. So we're going to take a look at recursive rules before we jump into example 2. A recursive rule for a sequence defines the nth term by relating it to one or more previous terms. The following is an example of a recursive rule. What they're going to do is tell you what the first term of the sequence is. So f of 1 equals 4, and then they're going to tell you the recursive rule, which is f of n equals f of n minus 1 plus 10 for each whole number n greater than 1. Now, this looks a little weird and funky and odd, and it's going to be a little bit confusing at first, but I'm hopefully going to be able to bring it all together. So the rule means that after the first term of the sequence, every term f of n is the sum of the previous term, f of n minus 1 and 10. Now, it's a little bit easier to understand once you see an example done and for me to run through it than me try to explain it from here. But one thing I want you to note the difference between explicit and recursive. Unfortunately, when I would go through and ask you what is the 15th term of the sequence, when I was dealing with an explicit rule, we could just plug 15 in. For recursive, you have to run through to get to the 15th term to be able to answer this. You cannot just plug in 15 for n and get your answer. So just know that for right now. And to note the difference, because they'll mix them in sometimes, explicit is when you just have n plugged in. A recursive is when you have f of n on the other side of f of n. So we have f of n equals f of n minus 1. If you ever see this f of n minus 1 or something n minus 1, what that is going to refer to is a recursive. If it's just n, then that's explicit. But if there's this f of n minus 1, that implies recursive. Now, like I said, it's going to be more helpful to kind of see it done than me explain it right here. So let's go ahead and take a look at example 2. Okay, for example 2, they ask us to go through and write the first 4 terms of the sequence. So much like we did with example 1 on the other side with the explicit rules, but instead this time we were dealing with recursive. So recursive is a little bit different. We're not just going to be able to go through and make a whole list of plugging in 1, 2, 3, and 4. Recursive is going to be a bit different. And again, recursive is anytime you see f of n minus 1, f of n minus 1. Whenever you see that, you need to do what I'm about to do. So let's take a look at A. For A, we have f of 1 equals 2, and then f of n equals f of n minus 1 plus 3. Now I know at first you're sitting there thinking like, oh, that looks like crap, and that's awful. It does, but once you've run through this once or twice, it's not too bad. So we have to write the first 4 terms. We've already been given the first term, which is f of n, or not f of n, sorry. F of 1 equals 2. They have already told us our first term. So our first term is 2. And you're done with the first term. Now to do the second term, so we're going to have f of 2 is going to equal, if I were to plug 2 into this, okay, so we have f of 2 equals f of 2 minus 1 plus 3. Well, 2 minus 1 is 1, so this becomes f of 1, and f of 1 is 2. So we're going to take the previous term, in this case 2, and we're going to plug it in for this f of n minus 1. So know that this blue part here, that I just highlighted blue, this f of n minus 1, that stands for the previous term. So we're on the second term, so our previous term is the first term, which was a 2. So we're going to plug 2 in for this here, and then do plus 3. So we have 2 plus 3. Now, you can't just go through and set up all the others. You actually need to solve these one at a time. So 2 plus 3 is going to be 5. And that's my second term. If we go to f of 3, so we're looking for our third term. F of n minus 1, 3 minus 1 is 2. So f of 2, my second term is 5. So we're going to take 5 plus 3, and we get 8. Now f of 4, if we plug in 4, we get 4 minus 1 is 3. So f of 3, my third term, is 8. So we're going to plug 8 in for that blue part. And we do plus 3 again, and we end up with 11. So my sequence, my first 4 terms for this problem is 2, 5, 8, and 11. So we're going to end up with 4 numbers again. So while it looks different at the start, once we get to the end it looks normal. Know that when you are dealing with recursive, and again to identify if it's recursive, you're going to see this f of n minus 1. What this part right here, this f of n minus 1, represents is that you're going to plug in the previous term that you just found. So they will always tell you your first term. So your first term in this case is 2. And then what this stands for is when you go through and find the second term, you need to plug in the previous term. So we're going to do 2 plus 3, we get 5. To find the third term, we're going to plug in 5. So we get 5 plus 3 is 8. And then 8 plus 3 is 11. So when you are dealing with recursive, it wants you to plug in the previous term you just found for this f of n minus 1. And then you can go through and solve. So unlike an explicit rule, where you just explicitly plug in the number for n, this one, being recursive, you have to go back and use the previous term. So let's go through and talk about one more, kind of on a basic level. If you look at b, for b they tell us f of 1 equals 7, and f of n equals f of n minus 1 minus 5. So what this means, again, this f of n minus 1 refers to the previous term. So we need to go through and find the first 4 terms of the sequence, and that's what we have to do. Sorry. So we have to go through and find the first 4 terms of the sequence. Again, you had to reuse the terms that you found to find the next term. So they always tell us our first term, f of 1 is 7, and I know that because they told me right there. Now f of 2, so our sequence is, or our rule, is f of n minus 1 minus 5. Again, I want you to think of this f of n minus 1. I want you to think of this whole part as the previous term. So our previous term is 7. So we're going to do 7 minus 5. And 7 minus 5 is going to give us 2. F of 3, we're going to plug in the previous term, which is 2. So we're going to have 2 minus 5. And we get negative 3. For the fourth term, again, f of n minus 1 minus 5. We're going to plug in the previous term for this f of n minus 1, so negative 3. Then we subtract 5, and we get negative 8. That's our answer. So the first 4 terms of this sequence are 7, 2, negative 3, and negative 8. And that is our answer. So anytime that you're dealing with recursive, you have to go through and do it a term at a time. Just know that f of n minus 1 means you're going to use the previous term in your sequence. Okay, so that's how we're going to do that for parts A and B for the recursive rule. Now, parts C and D are the similar idea. It's just the rules are a little bit more of a step up than just adding or subtracting a number to the previous term. So I'm going to move this up, and then we're going to take a look at C and D, just because they look a little different and it's helpful to see them done before we jump on to example 3, which as you can see is going to deal with some graphs. Okay. For part C, and let me move this down just a touch. All right. Part C, we have f of 1 is 5, and then we have f of n equals negative 3 times f of n minus 1 plus 12. Now, recall that this f of n minus 1 refers to the previous term. So we're going to have negative 3 times the previous term plus 12. So we're going to do negative 3 times whatever our previous term was plus 12. All right, they tell us our first term is 5, so f of 1 is 5. Now, if we go on to the second term, so f of 2, again, it's negative 3 times the previous term plus 12. So this is going to mean negative 3 times our previous term is 5 plus 12. Now, if you can do this and write it all out or in your head, great. I'm going to use my calculator just to show you where we get our answers from. So negative 3 times 5 plus 12 is going to give us negative 3. Now, our third term in the sequence, so f of 3, again, it's negative 3 times the previous term, which is negative 3, plus 12. So if I do negative 3 times negative 3 plus 12, I end up with 21 as my third term. Now, for the fourth term, again, it's negative 3 times the previous term, which is 21, plus 12. So we're going to do negative 3 times 21 plus 12, and we end up, whoops, I forgot the negative sign. So negative 3 times 21 plus 12. And I end up with negative 51 forgot the negative. So I end up with negative 51 as my fourth term of my sequence. So my four terms are 5, negative 3, 21, and then negative 51. And that is my answer for part C. So the reason I do that for part C is in case you see it being multiplied or divided, you know what to do first, instead of just straight adding or subtracting. So that is our answer for part C, 5, negative 3, 21, and negative 51. All right, now before I jump on to example 3, I do want to talk about D, just because it looks weird and because it feels weird, because it has a square root. And it's helpful to kind of see this one done, just that way you have an example of it. So for part D, we have f of 1 equals 65,536, and our sequence is f of n equals the square root of f of n minus 1. So what this whole thing here means is that we're going to take the square root of the previous term. So you're going to take your first term, take the square root of it, that's your new term. For the next term, you're going to take the square root of your previous term, that's your new term. So we're just going to take the square root of all the previous terms. All right. So again, I'm going to highlight this part means previous term when we do this. All right. First term, they have told us f of 1 is 65,536. So that is our first term. Now, f of 2 is going to be the square root of our previous term. So our first term, so my previous term here is 65,536. So we're going to take the square root of 65,536. Now, to take the square root, if you're using a TI-30, is you're going to push second, and then if you notice above the x to the power of 2 button, let me use something other than red. If you notice above the x to the power of 2 button, there's the little square root. Because that's in yellow, that means I need to hit the second button and then x to the power of 2, and that gives me a square root. So we're going to go through and do the square root of 65,536, and we end up with 256 as my second term. Now, f of 3, again, it's the square root of our previous term. So square root, my previous term, is 256. So square root of 256 is 16. And then my fourth term of the sequence, we're going to take the square root of our previous term, which is 16. And the square root of 16 is 4. So my first four terms of the sequence are 65,536, 256, 16, and then 4. And that is our answer for part D. So part D is not super hard, but it just looks and feels weird just because we have a square root of the previous term, and it just looks and feels different. So it's not that it's anything too difficult, just that it looks and feels different for us. All right. That is it for example 2 on dealing with recursive. So remember, explicit is where you just have f of n equals, say, 3n plus 2. So it's just n, so you can just plug in the number. A recursive is when you're going to see this f of n minus 1. And you have to go through and do what we just did for example 2. All right, example 3 is going to ask us to construct and graph the sequence described. And I'm going to slightly run out of room for this, but it'll work. All right, let's take a look at example 3a. So for example 3a, a pizza place is having a special. If you order a large pizza for a regular price, $17, you can order any number of additional pizzas for $8.50 each. Use the recursive rule. So again, recursive, which is f of 1 equals 17, and f of, let me highlight it first. F of n equals f of n minus 1 plus 8.5 for each whole number n greater than 1. Now, for this, we are dealing with recursive because I have this f of n minus 1. That means I need to treat this like example 2, where I use the previous term to go through for my sequence. Now, we're going to go through and construct and graph a sequence. So we need to go through and establish a sequence first. Let's talk about kind of a reasonable domain and range. It just has to be anything greater than 1. So that means 1, 2, 3, 4, 5, 6. That many numbers is kind of unnecessary for this one, and it's actually going to go off the graph if I go all the way to 6. We're just going to look at the first handful of terms, and let's treat it as the first 4 terms. Your homework might ask you to, it might give you a specific amount it wants you to go off of. If it does, just follow what it asks. So let's do the first 4 terms. So our first term is f of 1 is 17. So that's my first term. My second term, because this is recursive, f of n minus 1 plus 8.5, again, previous term, plus 8.5. So if I take my previous term, which is 17, I'm going to add 8.5 to that. And if we do 17 plus 8.5, I end up with 25.5. And then for the third term, just like we did in example 2, take our previous term, which is 25.5, and then add 8.5. So 25.5 plus 8.5 is 34. And then for f of 4, again, previous term plus 8.5. So 34 plus 8.5 is going to give me 42.5. So my first term is 17, then 25.5, 34, and 42.5. All right, so those are my first 4 terms. We just go through and plot the points. So my first term, so the number of pizzas, if I bought 1 pizza, it's $17. If I bought 2 pizzas, it's 25.5. If I bought 3, it's $34. And if I bought 4 pizzas, it's 42.5, which is going to be about there. And that is constructing my sequence, 17, 25.5, 34, 42.5, and then graphing my sequence for the situation. So that is how you do example 3. I just want to talk about B, just to kind of refresh our memory before we end for today. All right, so for part B, and let me cover this up so we're not distracted by it. For part B, it wants us to go through again and construct a graph, or construct and graph the sequence that it describes. So for part B, we have a gym charges $100 as the membership fee and a $20 monthly fee. It uses the explicit rule. So explicit goes back to example 1 of f of n equals 20n plus 100 to construct and graph the sequence. So we're back to explicit, which is example 1. Again, if you notice the difference between explicit and recursive, explicit does not have an f of n minus 1. So what this means is if I wanted you to find after 30 months how much it's going to cost, you can plug 30 in, you do 20 times 30 and do plus 100, and you have your answer. So remember, when we're dealing with explicit, you're not using the previous term, you're just using the term that you're on. All right, now for this one, a reasonable domain of numbers we could plug in would be 1, 2, 3, 4, 5, and 6. Now, to save some time from doing that step by step, each step of the way, I'm just going to show you from my completed notes what this looks like. So for B, again, I'm using this equation, or my explicit rule of 20n plus 100. And what I have done is I've just done it for the first, second, third, fourth, fifth, and sixth terms. Again, because we're dealing with explicit, that means I can plug 1, 2, 3, 4, 5, and 6 in. When you deal with explicit, you plug the number of the term you're on. When you deal with recursive, you have to plug in the previous term. So I got 120, 140, 160, 180, 200, 220, and then I just went through and plotted those points. Okay, so that is your video lesson for section 4.1, and that's kind of that. So if you have any questions, or if you want me to kind of run through something or answer anything that you're struggling with, just let me know the next time you see me, or shoot me an email. Otherwise, that is all that I have for you guys today. So thank you for listening. Have a great day. Be sure to use the completed notes as well when you go through and do your homework. So have a great day. I will talk to you guys later. All right, bye.